Assalamualaikum and hi, my name is Nurazian and my lab buddy Tivia. We are from Group 4 and we want to present about Analog Electronics Lab 2 Operational Amplifier using LTSpice.
Hi, good afternoon everyone. I am Divya Vijayan and my matrix ID is 251091683 and I will be presenting the results for 3 configurations from the Analog Electronic OP-AMP lab. The main objective of this lab was to understand the basic characteristics of OP-AMP circuits and compare our theoretical calculations against our LTSpice simulation results. I focus on 3 configurations, which is inverting amplifier, non-inverting amplifier and the summing amplifier. First of all, why is it called an inverting amplifier? It is called an inverting amplifier because the input signal is applied to the inverting terminal, which is positive terminal, and the output voltage is 180 out of space with the input voltage. Why is it called a non-inverting amplifier? It is called a non-inverting amplifier because the input signal is applied to the non-inverting terminal, which is the positive terminal of the OP-AMP, and the output voltage has the same phase as the input voltage. And finally, summing amplifier. What we can understand about summing amplifier? The summing amplifier or summer is an operational amplifier circuit that produces an output voltage proportional to the weight sum of multiple input voltage. All simulations use the LM741 OP-AMP with positive 15 voltage power supplies and 1 Vp and 1 kHz sine wave input unless otherwise noted. For the inverting amplifier, our feedback components were R1 equal to 1K and R2 equal to 13.3K, giving a theoretical gain of negative 33. For the second part, which is non-inverting amplifier, use R1 equal to 1K and R2 10K, that giving a theoretical gain of positive 11 voltage. The summing amplifier combine two 1 voltage signals using R1 10K and R2 2K and RF 10K. We observed the resulting waveforms and proceeded with the comparison and analysis.
For operational integrated circuit, it performs integration on the input signal. It uses a capacitor in the feedback bus to accumulate the input current over time. So for example, a square wave input will produce a triangular wave output. And for the operational of differentiation circuit, it performs differentiation on the input signal. It uses capacitor at the input to measure the rate of change of the input voltage. For example, a triangular wave input will produce a square wave output. So now, let's look at the basic rules of engineering that explain why our result turns out like this.
Starting with the inverting amplifier, our theoretical gain was negative 33, predicting an output of 33 voltage. However, the waveform was severely clipped. The division is explained by the non-ideal characteristic of output saturation. The OP-AMP output voltage cannot exceed its supply rails of 15 voltage positive, forcing the signal to be clipped at the limit. So, as an input, we will get a sine waveform and the output will be get as shown in the figure. Next, part B, non-inverting operation amplifier. For the non-inverting amplifier, the theoretical gain was positive 11, resulting in an expected output of 11 voltage, Vp. The simulated result was very close to this value and was not clipped, confirming the non-inverting gain formula. So when the input will be sine wave and the output also will be the same as a sine wave for the non-inverting amplifier. Let's move to the summing amplifier. Our theoretical output was calculated as negative 6 Vp, the weighted inverted sum of the two 1 Vp inputs. The simulated waveform visually confirmed both this amplitude and the inverted phase. The successful summation relies heavily on two fundamental principles of the inverting configuration. First, the virtual ground V equal to negative 0 voltage and the inverting input, which forces all input currents to sum at the node. And second, the OP-AMP's ideal infinity input impedance, which ensure all sum current flow entirely through the feedback resistor. A key trait of this circuit is its frequency constant drain. If we were to significantly increase the signal frequency, for example 3 kHz, the observed output amplitude would be decreased. This division is a result of the non-ideal OP-amp characteristic known as the limited gain bandwidth product. At higher frequencies, the OP-amp simply cannot maintain the required gain of 6 and the causing signal attenuation. The principle of negative feedback was fundamental, allowing us to accurately set the circuit gain. However, the non-ideal characteristic of finite supply voltage guided our interpretation of the clip results. The cause was demanding a gain of negative 33 with a 1 voltage input, and the effect was the OP-amp hitting to the 15 voltage supply rails. This demonstrates that the ideal OP-amp theory must be constrained by the physical supply limits. The cause of the summation is the application of the virtual ground principle, which decides that the input currents and the inverting terminal, and the effect is a scale inverted sum at the output. As a conclusion, we successfully validated the gain equation for 3 core FEMP circuits, which is inverting amplifier, non-inverting amplifier, and summing amplifier. The key lesson learned is that output clipping is critical non-ideal constraint, and the design must account for the OP-amp's positive VCC limits. The experiment strengthened my understanding of how real-world OP-amps like the 741 OP-amp behave, and why non-ideal characteristics such as supply voltage limits and finite bandwidth are crucial for practical analog electronics designs. That's all from me. Thank you.
First of all, our operation amplifier circuit rely on two key principles. The first one is zero input current, and the second one is virtual ground. This virtual ground principle is the fundamental reason we can use simple resistor ratio like AV equal to negative RF over Rin to calculate the gain for the inverting and summing circuit. Second, we learn about the gain versus bandwidth trade-off. Real operation amplifier circuit have fixed gain bandwidth product. This means if we want to increase the gain of the amplifier circuit, we automatically sacrifice some of its bandwidth, and the circuit will not perform well at very high frequency. Third, this trade-off also occurs in calculus circuit. So the differentiator circuit face noise issue at high frequencies. So this forces us to convert it into a practical differentiator. By doing this, we increase stability but trade off the circuit ability to handle the absolute highest frequencies. In conclusion, this experiment confirmed the 5 main functions of the operation amplifier, from gain amplification to differentiation and integration operations. So the main reflection is that analog engineering is about compromise. We must use our understanding of real operation amplifier constraints like input offset voltage, slew rate limits to ensure the design circuit is not only theoretically correct but also stable and reliable in the real world. Thank you.